I'm now recording. So just reviewing that we're going to measure the dielectric constant by using paper and aluminum foil. This is unit 2 progress check free response. And this is the relationship, of course. We're interested in K, and we've measured C, and we've measured A, and we've measured D, and we've got data in a table. Now, it always comes back to needing to get it into a y equals mx plus b situation in order to make a graph and then find what you're looking for. So they are thinking you're going to do this. So you're going to write it as c equals epsilon naught k over d times a, okay? And of course, this would be y, and this would be x, and this whole thing would be m. You guys cool with that?
Mm-hmm.
Okay, but of course we could also, and this is the other thing they're thinking, we could also go and do this as C is equal to epsilon naught K, oopsie, this is gonna be a little tight. We can fit it though. Epsilon naught, epsilon naught K A, and this is going to be our slope, times 1 over D.
One could also just isolate K and then have that be the slope alone, right?
Sure, you can do that too. But the point was I was getting to, so this is Y, this is M, and then 1 over D would be X. And my suggestion was, dude, why would we throw data away? We got data. I like data, right? That's why we're scientists, right? We've got the data. Why would we ditch the data? So because they gave us all that data, we could also rewrite this as C is equal to epsilon naught K times A over D. And we could use this as our Y variable, use this whole thing as our X variable, and then our slope would be that. Those are all legit, and then Yannis just pointed out another one. Well, while we're at it, why don't we just make it like this, right? And we're gonna do over here, epsilon naught A over D, right? And we're gonna make this our Y variable, this our X variable, and this is gonna be our slope. And then we get it directly off the graph. Yeah, without calculation after that. That's nice, right?
Beautiful.
Okay, and if you screwed this up and you ended up, for example, switching X and Y, you could still do that, but you would just get a slope and then you'd have to take the inverse to get back into the calculation mode. So any of these approaches is valid and they should take them, and that should include the data. So I think you can take all the data, and I would prefer that, but I think they're probably not leaning that direction. But yeah, so cool. I hope that makes sense. Good. Okay, indicate below which quantity should be graphed to yield a straight line. Vertical axis, horizontal axis, plot the data points for the quantities indicated. Okay, so let's go straight to the solution and let's see what they've got. Okay, they are plotting capacitance versus 1 over D. That's what they've got. So they've chosen to go with this option, right?
Mm-hmm.
Is it on there? Here. So they've chosen this option right here. And let's go and mark that in blue. This is the AP solution, but any of these is reasonable. So that's the one they've chosen. Okay. And they get that graph. I'm not going to redraw the whole thing, but we do see it's kind of a straight line. Nice. And we get that graph, and I had it a second ago. Here it is. Good. So we have a nice graph. It does look proportional, meaning it does go through 0, 0, pretty much, although they didn't draw it through there. And now the question is of finding the slope. And it goes pretty close through 8, 4. See that? So we could use that value. So slope is equal to 4 times 10 to the minus 5. Is that a 5? Is it? What is it? Is it not? Hang on. No, it's not. And what is
I think it's 4 times
8?
10
Is
to
it
the minus
8? Is
4.
it 8?
It's either -4 or -9.
I think -4.
It has to be -9. No, hang on a second. The biggest values they have. So if we take the top 4, it should be -8. It's an 8.
Oh, it is a -8. Oh, yeah.
Okay, so there's -8. And on the bottom, we've got
3.
8 times 10 to the 3.
Yeah.
8 times 10 to the 3 meters minus 1. Okay?
Mm-hmm.
Good. And then, of course, we've got that, and this is the option we've chosen. And boy, they've really chosen an option I think is pretty awkward because we've got all that stuff packed in there, but oh well. Plus, they had to calculate 1 over d, which is also awkward. So I don't know what they're thinking. I mean, if you're going to go with one option only, then that's a better idea, right? Because a is already given. Anyway, whatever. Okay, so let's see. There's 0.5, 10 to the minus 3, 10 to the minus 11. That would be 10 to the minus 12. 5 times 10 to the minus 12. And the unit here is farad meters. Oh, I'm not. Am I on the screen? Yes, I am. Okay.
Yeah.
-8, -11, -12, 5. 5 times 10 to the minus 12 farad meters is fine. And that would be the answer for this thing, epsilon naught k over, sorry, epsilon ka. So this is epsilon naught kappa times a. All right. And of course, that means kappa is equal to this number, 5 times 10 to the minus 12 farad meters. We're going to divide by epsilon naught. Epsilon naught is 8.85 or something. Is that right?
Yeah. Yeah.
8.85. What's the exponential on that? I can't remember that.
-12.
-12. Okay. And then the area given to us in this problem is, let's see, 0.25. Is that the one we're doing?
Yeah.
0.25 square meters?
Mm-hmm.
That's a big plate. It's 1/2 meter by 1/2 meter. Okay, whatever. Okay, somebody made up data. I mean, seriously, you're not going to use 1/2 meter by 1/2 meter, right? No, just me. That's like really big, right? I mean, like aluminum foil is not that big.
True.
The area is 0.25, so that's not the side length.
Well, but the side length would have to be 0.5 to get there, right? 0.5
Oh,
meters
right,
by
yeah.
0.5 meters
Yeah,
would be
true.
0.25. That's big.
Yeah.
That's too big. They made this up. This is not actually done. Oh, well. So there we go. Oh, the 10 to the minus 12 is canceled. That's good. The units we're just going to drop off because we're Americans. We talked about that earlier. 5 divided by 0.25 is 20. So this is 20 divided by 8.85. We can use our calculator. Okay, 20 divided by 8.85. I get 2.26.
Mm-hmm.
There we go.
And
Show
K
it.
doesn't have a unit. It's just
K does not have a unit. Very good
Okay.
question. So K is the dielectric constant that connects the permittivity of the dielectric to the permittivity of free space. So it's just a multiplier. And it's always bigger. It's bigger or equal to 1. Okay. So that's that. Plot the points, yada, yada, yada. Okay. Okay. All right. So our answer would be acceptable. By the way, they said 1 point is earned for indicating an appropriate subset of data to use that includes paper. 1 point is earned for a correct explanation. That's fine. Straight line. Okay. Got it. They got 2.26. So that's exactly the same number I have. Okay. And now, wait a minute, part E. On the axis below, sketch the capacitance C as functions of plate separation D, plate area A, and dielectric constant K. All right. Well, we could describe that. So coming back to here, this is our capacitance here, right? This is our equation, right? So we're going 3 ways on this thing, this way, and that way. Okay. Ooh. This is very efficient use of space, to say the least. So let's go over here. So here we have C versus D. Okay, assuming everything else is the same, as D becomes bigger and we do put more aluminum foil, paper in there, what would it look like? This kind of relationship is inversely related, right? So like this, yeah, that good? And then we have, they say, C varying with respect to A. Assuming D stays the same, it would be
Linear.
something like this. And then the other one would be C divided by K. Oh, okay, whatever. So if we increase K, the whole thing will be
Also
also linear. Okay, there we go. There we go. Okay. And I think those are good. I hope those are good. Concave up with the horizontal axis asymptote. Straight line, positive slope, straight line with positive slope. All right. Boy, we knocked that out of the park, didn't we? I feel very good. How did that feel?
Good.
Easy.
Easy? Good. So I actually, I'm glad I thought of these progress checks, because those were developed not for the test, but I think they were developed somewhat with a similar mindset as with the exam for this time, I think, to some degree, because they do tend to be a little more explaining and all those kind of things. I'm going to take a picture of the board, and we have 20 minutes. Wait, did I send this? Oh, wait, let's do this one. There we go. All right, here we go. Okay, cool. All right, good. Next thing, what's the next thing? Don't be shy.
Well, if no one has any requests, I did Unit 3 progress check, and I just wondered if we could have like a quick conversation about circuits again.
Okay.
Yeah.
So if you did it, but you were like, maybe that's a really good thing to look at. So let's do that.
Mm-hmm.
So yeah, circuits coming up. Oh yay! This is so exciting. Okay. Let's tape that up here. It's big enough, I think you can see it. Prints out nice and big. Maybe scooch a little closer. There we go. I think that's big enough, I hope. Maybe a little light. All right. Can you guys see that okay?
Mm-hmm.
Not really, right?
It's a little blurry at parts, but it's fine. It's recognizable.
That's crap. I'm just gonna copy it over here. This is just dumb. So there we go. That's better. Internal epsilon. Doing it like this, but I kind of like to kind of put the little, like it's a battery thing. You know what I mean?
Mm-hmm.
Remind ourselves about what that is. That's helpful for me. R2, R3, R1. This is point B. This is point A. This is switch S1. And this is switch S2. There we go. Und ist all right. Okay, here we go. So let's take a look what they got. In the circuit shown, the battery has an EMF of 10 volts. So we have 10 volts here. Okay. With an internal resistance of 0.2 ohms. Interesting. So they give you the internal resistance. And we have 3 resistors. R1 is 10 ohms down here. We have R2 is 5. And we have R3 is 5 ohms as well.
The picture is kind of going off to the right of the screen. Could you move it over a little bit, maybe?
Oh, great.
Thanks.
You're welcome. Maybe now I back up a little bit again. No, you're too close, Mr. All right. Did I send you guys a picture of my rig here, which is like, it's like you're on a chair, which is really funny. Anyway, professional videography looks different. Okay. Now we have a glare situation. Okay, good. Okay, so we've got the situation here. We've got a lot of things happening. Couple things. First of all, they like to complicate things a little bit, but generally there's only a certain degree to which they will complicate it. That's the first thing. Second of all, the basic ideas that you guys have to deal with are relatively straightforward because we don't have inductors. And thank God inductors are not in here because resistors and capacitors are relatively straightforward in terms of what happens. And the other thing of word of encouragement is most of the time it's just a question of having a big enough piece of paper and taking a deep breath and just having a sharp pencil and just not freaking out about anything. Then everything's going to be okay. Okay, so let's take a look what happens here. They ask for the voltage drop when both switches S1 and S2 are open, and they're looking for the voltage drop A to B. Well, that's cute. Sorry. So let's take a look, A to B. When, and actually just let's describe what happens. All the switches, both the switches are open. How much current flows through your circuit?
0.
0. No current flows. How about the segment between A and B? How much current flows there?
0.
0. If there's no current flowing through a resistor, how much voltage drop is there?
0.
Yeah.
0. So the relationship, of course, being, you can do it this way. This is the causal relationship that generally I prefer. But in this case, we're interested in how much voltage drop there is. And if there is no current through a resistor, then there is no voltage drop. You could have a current through something that doesn't have resistance, and then you could have a voltage drop. But if there is no current, then for sure, the voltage drop is 0. So the voltage drop between A and B has to be 0, and this is part A. Delta V is equal to 0, and that would be 5 ohms equals 0 volts. Voila! Pretty straightforward, right?
Yeah.
Yeah, good. So let's take a look. Part B. Calculate the magnitude of the voltage drop AB when switch S1 is closed. Okay, now we're closing just S1. Whoop! And we'll take a look at our circuit. Now, a couple things can happen here. You can forget about the internal resistor. Don't do that. But otherwise, it's really straightforward, right? Because if you look at the overall resistance, that's probably a good approach, because once this switch is closed, how much current, where does the current flow? Just through the left loop, right?
Mm-hmm.
Because over here, no current can flow because the switch is open. So this is all that's happening. And that means over here, it's a straightforward 1, 2, 3 resistors in series, right? So this would just be R1, whoopsie, sorry, R internal, okay? Then this is R2, and that's R1, okay? So that's 15.2 ohms, 0.2, 5.2, 15.2, good? And then of course the current, whoopsie, what are they asking? Voltage drop, sorry. Voltage drop AB equals the current that flows times the resistance. Now the current we'll have to get first, and the current is of course the total voltage, which is 10 volts, divided by the total resistance, which is 15.2. Hope it's okay I put that together. So now I've got the expression written here, conveniently down here so you can't see it. So this is the current, and then we have the resistance of between points A and B, which is 5 ohms. There you go. And we get like 3.2 or something, 3.3, something like that.
Yeah, 3.3.
3.3 volts. So the voltage drop, and they write it like this, but generally we prefer to write it like this. So delta VAB is 3.3 volts. And then before it was 0. Let me guess, they're now going to ask what happens when we close the other switch. But let me just ask you this way, rather than determining it, because that would be not something that's going to happen tomorrow. But they could ask you what will happen to the voltage drop across AB when we close switch S2. So S1 was closed, okay? And now we close switch S2. What will happen to the voltage drop AB? Will it increase? Will it decrease? Or will it stay the same? And explain.
Wouldn't it stay the same?
Yeah, it stays the same. Because they're parallel.
Well, Kirchhoff's loop rule, so it still needs to drop the same amount of voltage over the whole circuit. And it's not like the other resistors changed, so it still needs to drop the same amount from A to B.
I mean, our total decreases because we have
Our total
parallel.
certainly decreases. That's definitely true. Agreed?
Yeah.
Our total decreases. So what happens to the overall current?
Increases.
Increases. The total current increases. You guys agree?
Mm-hmm.
Yep.
Okay. Total current increases. Now, the total current increases. Does all the current go through R2?
No.
Does half the current go through R2?
Yes.
Yeah.
Yes. Okay. Does all the current go through R1? the current going through R1 has increased.
Yes. No.
Yes.
Oh, yes, yes.
Overall current goes up because the overall resistance has decreased. Therefore, we're now pushing more current through R1. Do you guys agree?
Mm-hmm.
If we push more current through R1, what will happen to the voltage drop across resistor R1?
Be greater.
Will be greater. Now, more voltage drops across R1. If we apply Kirchhoff's loop rule to the left loop,
Mhm.
which we still can, yeah? What will we see now that the voltage drop across R1 is bigger and the voltage drop across little r is also bigger? What's true of the voltage drop across R2?
Smaller.
Smaller. So the voltage drop across R2 is smaller because it requires more voltage to push the current through the two resistors that are in series with the power supply.
But we're not talking about the voltage drop across R2. We're talking about the voltage drop across A to B, right? So that includes R3.
No. Well, yine.
Uh,
So
It's at
the
the
voltage
junction.
drop from A to B is the voltage drop from here to there. And just a reminder what we have here, this is the top of the slope, right? So before, skiers could only go down this way. Now you've opened up another slope over here, so skiers can go down this slope, or they can go down this slope. But both slopes lead from the top of the hill to the bottom of the hill. Every analogy breaks down at some point. Our ski slopes, ski hills vary in height. In this case, this hill has become shorter because this hill down here has become bigger, but this total height for your whole ski resort system is still the same because your ski lift is only lifting you 10 volts. You're dropping a certain number of volts on a little resistor, which we can almost ignore, a certain number of volts here, and a certain number here. Those three numbers together need to add up to 10. The same thing has to be true of this, this, and this, because we can also make a Kirchhoff's loop rule for the big loop. So we could also apply Kirchhoff's loop rule this way. And then you'd see also a couple things. You'd see that the voltage drop through the little resistor internal, plus the voltage drop through R3, plus the voltage drop across R1, totals the voltage lift you're receiving from the lift, from the power source or battery.
Mm-hmm.
So this is the point where you ask more questions if that's still shaky for you. And don't feel ashamed.
It makes sense.
It makes sense? Okay, good. Hannah?
It does, but what confused me about this problem was thinking about the voltage drop from A to B as either going through only R2 or only R3. And then if it went through, like if current traveled through both, then I got confused.
Right. No current travels through both. That's really the
Okay.
key here, because that's why that ski resort analogy is helpful, for me at least.
Mhm.
You think about the lift drops you off here, then you
Mhm.
all go down a little hill. You got to go through this little hill. This is this one. And then you kind of have a plateau. And then when the switches are closed, you have a choice. This might be like a blue run, and this might be a black diamond run or something. Two different runs, but they both get you down to the little Almhütte here, where you can have a hot cocoa, and then you can take a break. And then if you want to ski more, then you get down, you ride down the last, that one everybody has to go down. There's only one choice. And then you get back to the bottom where the ski lift is, or you say call a day and go back to the hotel.
Okay.
Okay? So that's
So
basically
current
yeah.
travels either through R2 or R3.
Correct. Yes. So again, current is electrons. So if an electron has traveled through this one, then I mean, if they went back up here, they would be where they started. So again, the idea is that the skiers start at the bottom, get lifted to the top by the ski lift, and then make their way back down to the bottom. I mean, theoretically, you could like ski down this way and then like walk up this hill, you know, and but that's not a good way of using a ski resort.
But doesn't only half the current flow through R2?
True.
So doesn't the other half flow through R3?
Yes.
Okay.
It
But when you
does.
think Kirchhoff's
does.
loop, okay. See,
Yeah.
this is what confuses me.
Yeah. So Kirchhoff's loop rule only addresses what's happening with the voltage, not what's happening with the current.
Mhm.
So the current, you'd have to use Kirchhoff's junction rule. So
Yeah.
Kirchhoff's junction rule says, for example, let's use purple, maybe, or orange, or maybe black. I'm going to use something like black. We don't really have black. So we now apply Kirchhoff's junction rule right here. Right, at that point, then we'd see, okay, the total current comes in here. We'll call this I, right? And then two currents come out of there. One goes here, call that I3, and call this I2. Then it would be true. Kirchhoff writes it like this: incoming is plus, and the other ones are negative. And the total current is equal to 0 at a junction. But you generally write it like this, and that's totally fine, is that the incoming currents equal the outgoing currents. Either one of those is fine. This is Kirchhoff's junction rule applied at that point. This is also Kirchhoff's junction rule applied at that current, just written differently, okay? So either one of those approaches is correct. The total current is conserved because circuits neither create nor destroy charges. Therefore, all the current that comes into this junction needs to split. The skiers get a choice. The better skiers go down the black diamond. The not as good skiers go down the blue run. Everybody gets a hot cocoa in the middle. So that's how we're doing this.
Okay.
Okay?
Thank you.
Okay. Well, let's take a look. So, right, A, B, and then C, we can actually find the value. If we wanted to do that, you'd have to find the overall resistance and figure out the current, and half the current goes through there, and then yada, yada, you got it. But they have a solution printed there. I think this was more of a conceptual issue. So let's take a look where we are. Oh, okay, now they also vary it where they have S1 open and S2 closed. Well, that's cute. That's dumb. Why is that dumb? So they
Doesn't
want
it
to
just close off the circuit?
It's still
not
it just knocks out the circuit. S1 controls whether the circuit works at all. So once S1 is open, it doesn't matter whether S2 is open or closed. That doesn't make a difference. So they want to toggle the S1 and S2 into 4 combinations, right? On, off, on. There were the four possibilities. So they go through them, but really at that point, we again have no current. And I don't know if this will like lead to more wrongness. You know, I'm not sure why they're asking this, because I think students who got the first one wrong will get this wrong again, and the first students who got the first one right, where they were both open, will get this one right as well, I think, but I'm not sure. Maybe not. Okay, now we're going to bring in the capacitor. Aren't we excited? Okay. And capacitor. Okay, so we're putting a capacitor now down here instead of having this guy down there. So this is now not R1, this is now capacitor C. Okay. Okay, I see. Okay, so we are going to have S1 closed, but S2 open. So our initial setup, wow, this is really messy. I'm gonna hold this up for you. So our initial setup has S1 closed and S2 open. And that, of course, means that initially, wow, this is so high tech. Aren't you glad I'm doing this so high tech? Wrong side, Blessman. Over here. Oh, I'm really bad at this. Okay, so here we go. So this part of the circuit is just gone, right? So this is our circuit. It's a straight up circuit, R2 and then C. And then little r, of course, is there as well. Now, as we let this thing pass and charge, eventually the capacitor will be filled up. Okay?
Mm-hmm.
When the capacitor is filled up, what is the voltage drop across the capacitor?
10 volts.
It is 10 volts, okay? Because there's no longer any current flowing, there are no voltage drops across any resistors. All the voltage drops across the capacitor, okay? And you might be like, are there times that that's not the case? Yes. We've seen resistors, a capacitor in parallel, for example, with a resistor. You could have a situation where there is a voltage drop. And this is actually important enough. I'm just going to make a quick drawing of that because, yeah, because I want you not to get that wrong. So, all right, I think, and I don't know if I already sent you this or not, but here we go. Good. So let's erase that because this is so mega messy. Good. So when we close this, whoa, that's really big. There we go. We close that switch, current flows here, and of course, technically no current flows through here, but instead what's happening is that the pump, which is this thing, right, the battery, will grab an electron from here, right, move it through there, and then deposit it over there. And then we have a kind of a electron hole on there. Yes?
Mm-hmm.
It is holy. Ha, 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 ha. Love my holy jokes. Okay, so here we go. There we go. All right, there we go. We've built this thing up. We built a field in that direction, edge effects, all good. And of course, the charge on here, delta V times C, C is constant. So all that matters, if we're asking how much charge piles on here, we're asking effectively, what is the voltage drop across that thing? And because after steady state has been reached, after this thing has been closed, no more current can flow because the capacitor is blocking off the whole circuit because it's in series with the battery, right?
Mm-hmm.
If we had placed this capacitor there, right, then there would be still some current flowing even after the capacitor is full. And then therefore, the voltage drop would not be the full voltage drop of the battery in steady state. Okay? Does that make sense?
Yeah.
Okay, good, good. So if we had moved it over here, there would be a small voltage drop over here, and then this capacitor over here would not have the full voltage drop. It would have like 9 volts or something, or 9.5 or something like that. Therefore, it would have less charge on it. I don't know if they asked that for part F, but if they're doing that, then that's a good question. I would like that. I don't know if they would, though. I don't think they're asking that. So, okay, cool. And we are actually slightly past the time that we were saying we're going to spend on here, but I think we did a good job, and I hope you guys understand that unit a little bit better as well. That also puts us in the position, I think, that tomorrow we should be able to make our way through, I think we only have two or three of these progress checks left. And then we would have worked all our way through those 8 free response questions as a final review, which I feel pretty good about. And then you guys can rock that AP exam tomorrow night, which is going to be so cool when you rock that thing.
Sounds good.
I believe in you.
Thanks.
Thank you.
Okay, so I'll stop recording.